Let's talk about how we can use formal charge to decide between multiple possible Lewis structures for a molecule. The rule of thumb is that the best structure is going to be the one that minimizes the formal charge on all atoms. So in instances when we need to, for instance, decide between different possible connectivities of atoms in a molecule, we can use formal charge to help us out. For example, CO2, we can write the connectivity of atoms as OCO with carbon as a central atom, or COO with oxygen as a central atom. And once we complete the Lewis structures and calculate formal charges, we will see that one of these minimizes the formal charge on all atoms. That's the carbon as a central atom. And of course that fits the physical reality. CO2, carbon dioxide, which is normally found in the atmosphere and stable, has carbon as a central atom, whereas the other possible connectivity is not found. Secondly, we can use formal charges to help us decide when various possible resonance structures are possible for a molecule and those resonance structures are not equivalent. We can use a formal charge to decide which one is the best one to represent that molecule. So for instance, N2O has this resonance structure with a triple bond between the nitrogens. We could also represent it with two double bonds, and we can represent it with a single bond between the nitrogens and a triple bond between oxygen. If you go through the process of writing out this Lewis structure for this molecule, and I encourage you to do that using the step-by-step method that's illustrated in your book and in previous videos, what you will find is that you can come to these possible resonance structures, and of course these resonance structures are not equivalent. Right? They don't look alike. They have different ways of representing the triple and double bonds. Which one then is going to be the best representation for our structure? Well, we can use formal charge to make that assessment. And then finally, we can use formal charge to decide how far to expand an octet. So for instance, SO42- has this Lewis structure. Okay. Now, this is a perfectly fine Lewis structure. We have octets on all atoms, including the sulfur, the central atom. However, sulfur can have an expanded octet. It is below the second row of elements in the periodic table. It can expand past 8, and so we could, without breaking any rules, rewrite this structure to include a double bond between the oxygen and the sulfur. Now oxygen has 10 electrons around it, not just 8. However, since it can have expanded octet, that's actually okay. We could continue. We could, instead of writing just one double bond, we could put 2 double bonds between oxygens and sulfurs, or even 3 or 4. Well, how do we decide when to stop when expanding the octet on a central atom that allows it? We will use formal charge, calculate formal charges, and then see which structure minimizes the formal charge. So back up to example number 1 on deciding between different possible connectivities. If we complete the Lewis structures as shown, we calculate the formal charge. Oxygen has 6 valence electrons, and the first oxygen up here has 4 electrons in lone pairs and 2 electrons in bonding pairs. So that's 6 minus 4 minus 2, so 0 formal charge. And we find that the carbon also has 0 formal charge and the oxygen 0 formal charge. And I encourage you to go through that calculation to show for yourself. In the other representation with the different connectivity, we find that the formal charges are minus 2 on the first carbon. Carbon has 4 valence electrons. It has 4 lone pairs of electrons, or 4 electrons in lone pairs, and then it has, of course, 4 electrons in bonding pairs to it. 1/2 times 4 is 2, so 4 valence minus 4 minus 2 in bonding pairs is -2 for the formal charge. The central oxygen, using the same type of calculation, has a +2 formal charge, and the last oxygen has 0. Notice that the formal charges are very high in the molecule on the right, whereas they're all 0 on the other combination of connectivities, and therefore the first molecule is the preferred one and will likely be the more stable structure, which it is. And then in example 2, on deciding between various resonance structures, the N2O case, if we calculate the formal charge, we find that in the first structure we have 0, +1, and -1. Please pause the video and take some time and verify those calculations. In the second molecule we have -1, +1, and 0. So similar, although on different atoms. In the final structure, we have -2 on nitrogen, a +1 on the central nitrogen, and then a +1 on the oxygen on the right. Therefore, for this structure, which has by far much higher formal charges than the other two, that structure we can rule out as being less desirable. And since the other two have equivalent formal charges, we're going to circle those as being the best structures. We will talk about a way to even possibly distinguish between these resonance structures which have similar formal charges in another lecture. And then finally, on deciding how to expand octets, in the sulfate case, if we calculate the formal charge on the oxygens in the first structure, we find they're all -1. For the sulfur, it's +2. By moving in one lone pair of electrons to form a double bond, now we have -1 formal charges on 3 of the oxygens, the 3 that we didn't move in lone pairs. The oxygen on the right, in which we moved the lone pair, its formal charge drops to 0. And for sulfur, it goes from +2 to +1 formal charge. If we move yet another lone pair in, as on the third structure, we find 2 oxygens have a -1 charge, a formal charge, and then 2 oxygens have 0 formal charge. In addition, moving 2 pairs of electrons in on the sulfur reduces its formal charge to 0. So even though we have a lot of electrons around the sulfur, it can have an expanded octet that is allowed, and the structure which minimizes the formal charge is this one, and so we will take that to be the best representation of the molecule. And by the way, if we moved in another lone pair from a third oxygen, what we would find is that the formal charge in the sulfur would drop by another -1 to become a -1 formal charge, and therefore expanding further will not be lead to better structures.